Alright, welcome to our review for Exam 2, Calc 1. Let's go ahead and get started. First here we are taking a derivative of y to the 6th power where y equals a function. So this is power rule for functions. Now remember, power rule for functions says if you differentiate a function g of x to the nth power, so we're going to do prime of that, then you get n times g of x n minus 1. So exponent comes down, decrease the exponent, times the derivative of the inside function g prime of x. So that's what we're doing here. So the 6 comes down in front, times y to the 5th power, so just like a regular derivative, but then the inside function is y, which is f of x. So times the derivative of the inside, y prime or dy dx. And here we're doing a derivative of a composition here, f of g of x. And remember, if you differentiate a composition, that you get the derivative of the outside function f prime at the inside, g of x, times the derivative of the inside function, g prime. So the derivative of sine x here is cosine of x, except we're putting in x cubed. So cosine, plug in x cubed, and then times the derivative of this inside function, 3x squared. Two interpretations of the derivative. Number one, slope of the tangent. And number two is instantaneous rate of change. So this has to be instantaneous. Instantaneous rate of change of y with respect to x. And then instantaneous velocity is one special case of that. So these were the two important ways to interpret the derivative function. And then the definition of the derivative. Now the definition of the derivative is the limit definition. You need to know this. This was the limit as h goes to 0, f plug in x plus h minus f plug in x, and then divide by h. So remember, this came from slope of a secant line. This is the difference of the y's on the top, and the h stands for the difference of the x's on the bottom, and we're letting the difference of the x's go to 0. And then we're going to use the definition. Using the definition, so using this limit definition, we want to find the derivative of negative x squared plus 2x plus 4. So there's one problem where I want you to use the definition. So you can double check using the formulas. F prime of x, we know from the formula, should turn out to be negative 2x plus 2, just using the power rule. Negative 2 comes down, decrease your exponent, derivative of 2x is 2, derivative of 4 is 0. So this is the answer we should get when we're done, but you need to use the definition or you're going to lose most of your credit, because the point of this problem is to test the definition. So let's set up our f prime here. F prime of x then is equal to the limit as h goes to 0, f plug in x plus h minus f of x, and then divide by h. So that's this definition here. I'm just carrying that down. Now, our f plug in x plus h, here we've got a polynomial. So let's go ahead and plug in and simplify that. So f plug in x plus h. Let's write our polynomial with empty parentheses here. So this is going to be negative parentheses squared plus 2 times parentheses plus 4. So I just rewrote it with empty parentheses in place of x. And what's going inside there is x plus h. So x plus h squared plus 2x plus h and plus 4. And then we want to simplify this as much as we can. So this is going to be negative. We'll have x plus h times x plus h. And then let's see, we can multiply the 2 in times each term here. So plus 2x plus 2h and then plus 4. And now let's FOIL here. So first terms are going to give, we've still got a negative out in front, x squared. Outer terms xh, inner terms xh, so plus 2xh. And then last terms h squared. And we're going to have to remove the parentheses and change the signs in a minute. Plus 2x, plus 2h, and then plus 4 on the end. Okay, so now let's go ahead and remove the parentheses, change our signs. So negative x squared minus 2xh minus h squared plus 2x plus 2h and plus 4 on the end. And it looks like everything is simplified. We've combined all our like terms. So we're going to plug that in right here. So this will now be limit h goes to 0. And this whole thing plugs in for f of x plus h. So we've got a negative x squared, negative 2xh, negative h squared, plus 2x, plus 2h, and plus 4. And then we're subtracting off f of x. So minus our f of x is here. Negative x squared plus 2x and plus 4. And that whole thing divided by h. Now to subtract, you change the signs and add. So let's change this to positive, negative, negative, and then we'll add. So to subtract, add the opposite. And then we've got a lot of cancellations that go on here. Negative x squared, positive x squared, positive 2x, negative 2x, positive 4, negative 4. So this all simplifies to limit as h goes to 0. And we've got the negative 2x h left and the negative h squared and the plus 2h over h. Now this is still form 0 over 0, but we should get an h to factor out and make this h on the bottom cancel. That should always happen. So this will be limit as h goes to 0. Factor an h out on top. Negative 2x will be left here. Take 1h out here, negative h is left. Take the h out of here, plus 2 is left. And divide by h. And now h divided by h is 1, so those cancel. And we are just looking at the limit as h goes to 0 of negative 2x minus h plus 2. And now this is a polynomial, no longer 0 over 0. We can plug 0 in for h and get our limit. So it's just going to be negative 2x minus 0 plus 2, negative 2x plus 2, which is what we got from checking with the formula. So you can use the formula to check, but you're going to have to evaluate this limit on one problem. All right, next up we are computing some derivatives but not simplifying. So it'd be a little bit of a time saver on the exam. So here remember this notation, d2y dx squared is telling you to take two derivatives, and then the vertical bar is telling you to evaluate at x equals 1. Okay, so here's our y. So let's go ahead and figure our two derivatives, and then we'll go ahead and we'll plug in our x value. Okay, so y prime or dy dx, the first derivative here. This is going to be a couple of power rules here. So negative 4/3 comes down in front times the 5. So negative 4/3 times 5. And then subtract 1 from your exponent. So negative 4/3 minus 1 would be negative 4/3 minus 3/3. That's negative 7/3. And we need an x in there, x to the negative 7/3 power. And then negative 3 comes down in front times the negative 2. It'd be positive 6 times x. And then again, subtract 1 from your exponent. So negative 3 minus 1 would be negative 4. There's our first derivative. And we could combine these together, negative 20/3 if we want. So this would be negative 20/3 x to the negative 7/3 plus 6x to the negative 4. And then our second derivative, y double prime, which is what this is, d2y dx squared, y double prime is going to be negative 7/3 times negative 20/3. So that exponent comes down in front times x, and then again decrease our exponent by 1. So negative 7/3 minus 1 being negative 7/3 minus 3/3, negative 10/3 power. And now negative 4 times negative 6 being negative 24. Subtract 1 from our exponent again, so that goes more negative, be negative 5 power, negative 4 minus 1. And then we can simplify those guys, multiply them together. So negative times negative is a positive. 7 times 20 is 140. Over 3 times 3 is 9. And we've got an x to the negative 10/3. And then minus 24 x to the negative 5. Now we want to evaluate at x equals 1. Okay, so that's saying what is y double prime at 1 would be a different way to write that. And so all we're doing is plug 1 in here for our x. So this is going to be 140 over 9 times 1 to the negative 10/3 power, and then minus 24 times 1 to the negative 5th power. But 1 to any power is just equal to 1. So all we need to do here is this is a 1 and this is a 1, and we just need to subtract 140 over 9 minus 24, which is equal to negative 76/9 if you do the calculator work there. Alright, and now we're differentiating here one function divided by another function. So I look at this and I'm thinking quotient rule here. My f is going to be the top function here, root t minus t cubed, and then the bottom function here is going to be my g. So let's go ahead and find our f prime and our g prime. So the derivative of the top, well, let's see. We want to actually, let's rewrite this for a second here. This is going to be derivative with respect to x, and we don't have a root rule, but we've got a power rule. So let's write that root t as t to the 1/2 power, and then minus t cubed, divide by secant t. So now to do our f prime, 1/2 comes down in front, times x, and then subtract 1, I'm sorry, t is our variable here, times t, and then subtract 1 from our exponent, so negative 1/2 power. And now 3 comes down in front times that negative 1 will be negative 3. And t to the negative 3 minus 1, negative 4 power. And then for our g prime, the derivative of secant, remember, is secant tangent. So this is secant t tan t. So make sure that you know all those derivatives of trig functions that are on the study guide. And then what do we want to do here? Well, we want our f prime g minus f g prime all over g squared. So f prime is right here. So we're going to have a 1/2 t to the negative 1/2 minus 3 t to the negative 4, and then times our g, which is the bottom function here, secant t, minus f, which is the top function, t to the 1/2 minus t cubed, and then times g prime. So our g prime is right here, secant tangent. So times secant t tan t. And then downstairs we divide by g squared. So g is secant. So we're going to divide by secant squared t. Same thing as secant t squared. And we are not simplifying, so we're done. We did a product rule, we don't have to simplify. Here we want to find h prime of x if h of x is sine x times x to the 5th plus 3x squared. So I see a product of two different functions here, so I look at this and I see an f and a g. And let's go ahead and figure our f prime and our g prime off to the side. Remember, product rule here, we're going to do f prime times g plus f times g prime. So f prime, the derivative of sine x is cosine x. G prime, derivative of x to the 5th is 5x to the 4th, power rule. And then 2 times 3 is going to be 6, x to the 1st, decreasing our exponent by 1. So there's our f prime, g prime. So f prime is cosine x times our g, which is right here, x to the 5th plus 3x squared, and then plus f, which is sine x, times our g prime, which is down here, 5x to the 4th plus 6x. Done. We don't have to simplify. Okay. If you want to insert some extra parentheses around your trig functions there, that's okay. So we had quotient, we had a second derivative, we had a quotient rule, we had a product rule. Now in part D we have a combination here. We've got that root there. Remember, roots you always change to powers. So this is derivative with respect to x. And this is the same thing as x cubed plus 2 divided by x minus 1. And then that whole thing gets a 1/3 power. Remember, cube root is 1/3 power. So this is going to be power rule for functions. We've got a function to the 1/3 power. So the 1/3 comes down in front. Remember what that rule is again. Going back up to the top here. N, g of x, n minus 1, derivative of the inside. So the inside stays the same when you bring the power down and decrease the power, and then times the derivative of the inside. Lots of students want to put g prime on the inside here, but that's not right. The inside function stays the same, and you multiply afterwards by derivative of the inside. Okay, so what I'm doing here is I'm doing n times g of x, n minus 1 power, times g prime of x, derivative of the inside. So the n is 1/3. So 1/3 comes down, inside function stays the same, x cubed plus 2 over x minus 1. And then subtract 1 from your exponent, so 1/3 minus 1, negative 2/3, and then times the derivative of this inside function. So times the derivative with respect to x of that inside function, x cubed plus 2 over x minus 1. Now, to do the derivative of the inside function, this part here, we have to do a quotient rule. I see a quotient of two functions here. So let's do that down here, and then we'll go ahead and plug it in. So derivative with respect to x of x cubed plus 2 over x minus 1. So our f is up on top here, and our g is the bottom function, x minus 1. And so we want to do, again, f prime g minus f g prime all over g squared. And then we'll plug that in up here. So f prime, the derivative of the top, 3x squared is the derivative of x cubed. And derivative of 2 is 0, times our bottom function g, which is x minus 1, minus the top function f, it's x cubed plus 2, times the derivative of the bottom function. Derivative x is 1, derivative negative 1 is 0, so that's just 1. And then divide by the bottom function squared, which is our x minus 1. So x minus 1 downstairs, and that guy gets squared. Okay, so this whole expression here goes right in here. So this derivative then equals 1/3 comes down in front. Inside the function stays the same, x cubed plus 2 over x minus 1. Decrease the exponent by 1, negative 2/3 power, times the derivative of our inside function. And you don't have to do any simplifying. Just leave it 3x squared times x minus 1 minus your x cubed plus 2. We don't need to do the times 1. We can leave that out. And then divide by x minus 1 squared. Okay, we're not requiring any simplifying. All the differentiating is done. Okay, once you take in derivative of the inside, we have a derivative. It's not simplified, but that's okay. And then part E here, this one is a composition. So we've got cosine, and then we're plugging in the cosine of x squared plus 5. So actually this one is a double composition. You got to be a little bit careful. See here our outside function is f, and then our inside function g of x is cosine of x squared plus 5. So this whole thing is our inside function. And remember, when you find the derivative of a composition like that, you do f prime, derivative of the outside, plug in the inside function, g of x, and then times the derivative of the inside, g prime of x. So derivative of the outside function, cosine, is negative sine. Plug in the inside function, so this inside stays the same, cosine of x squared plus 5. And now times the derivative of the inside function. So this is our g of x. We have to do derivative of the inside. So times the derivative with respect to x of this inside function, which is cosine of x squared plus 5. Okay, now again, let's pull this off to the side, work it out, and then we'll plug it back in. So the derivative with respect to x of cosine of x squared plus 5, well, this is a composition. Okay, we've got an f, plug in g of x. Okay, it's not multiplication, but it's an f of g of x, and we're doing the prime. So again, this is going to be derivative of the outside, f prime, plug in the inside, g of x, times the derivative of the inside function, g prime of x. So here our outside function is cosine, our inside is, our smaller inside here is x squared plus 5. So derivative of the cosine is negative sine. And then we're plugging in the inside function. Inside stays the same, x squared plus 5. Now times the derivative of this inside function. So derivative of x squared is 2x. Derivative 5 is 0. Okay, so here is our expression for the derivative of the inside. So we're just going to plug that in here and we're all set. So this is going to equal negative sine of the cosine of x squared plus 5. And now times the derivative of the inside, which is right here. So times negative sine of x squared plus 5, and then times 2x. And we're done. So there we had to use 2 chain rules. So these problems are representative of, the types of problems I can give you. I can't really conceivably give you one question of every single kind. But here, we got a product rule, we had a quotient rule, we had a second derivative. Here we had a quotient rule and a power rule. Here we had 2 chain rules. So there's lots of possibilities here, but these examples are representative. You want to make sure that you review your homework problems from this chapter and try to work some more problems. And work on the other practice exam at a minimum. Okay, next up we are doing some implicit differentiation. So x plus xy cubed equals 1 minus y quantity to the 4th. And we remember here that y equals f of x. Y is a function. So when you differentiate x, you get 1, but if you differentiate this y, you get y prime, or dy dx. Alright, so we want to take derivatives of both sides. So the 2 sides are equal, so then the derivative of this x plus xy cubed is going to be equal to the derivative with respect to x of the right-hand side, which is that 1 minus y to the 4th power. So left-hand side, derivative of x, that's a regular derivative, so that's 1. And then derivative of x times y cubed, that's going to be a product rule. So this is our f, and then our g is y cubed. So this whole thing here is our g. So then we want to find, bring our 1 down, we want f prime g plus f g prime. You don't have to write out the little rules underneath if you don't need them. If it helps you, go ahead and do it, but I'm just trying to let you see my thinking process. So the derivative of f is 1 times our g, which is y cubed, plus f, which is x, and then times g prime. The derivative of y cubed is going to be 3y squared, but then again, this is a function to a power. Remember, y equals f of x. So we have to multiply by the derivative of the inside function. It's power rule for functions. So times y prime. That's the derivative of this inside function y. So that's the left-hand side derivative, equals, and then the right-hand side derivative, this is a function, 1 minus y to the 4th power. So power rule for functions. So 4 comes down in front, times 1 minus y, decrease your exponent by 1, and then times the derivative of this inside function. So derivative 1 is just 0, and the derivative of negative y is, if this was negative x, the derivative would be negative 1, but it's negative y. Derivative of y is y prime. So this is 0 minus y prime. Now we have 2 terms right here and here that have y primes in them. Let's do a little bit of simplifying and then we'll solve for y prime. So 1 plus y cubed here. Yeah, 1 plus, we don't need 1 times y cubed is y cubed. So 1 plus y cubed. And then plus, why don't we write this as 3xy squared times y prime? So 3xy squared y prime equals, and let's go ahead and simplify over here a little bit. This negative sign right here, 0 minus y prime is just negative y prime. That negative sign we can go ahead and pull out in front. So negative 4 times 1 minus y quantity cubed. And then we factored this negative out, so all that's left there is times y prime. And now here's a y prime term, here's a y prime term. We want to get those on the same side. So why don't we go ahead and pull this over on the right hand side as a negative. So 1 plus y cubed is going to be left on the left hand side. Equals, and then this 3xy squared y prime is going to come over as a negative. So we'll have our negative 4 1 minus y cubed times y prime. And then this will come over to the negative minus 3xy squared times y prime. So now our y prime terms are on the one side of the equation. And then notice y prime is a common factor. So we can factor out that common factor. So let's take this up here. So we've got a 1 plus y cubed on the left hand side equals, and then we can factor y prime out of here, and we'll have a negative 4 times 1 minus y cubed left. So negative 4 times 1 minus y cubed. And then factor the y prime out of here, we'll have minus 3xy squared. So minus 3xy squared. Okay, that whole quantity is times our y prime. And so now this is multiplied by the y prime. To get y prime all by itself, we have to divide that whole thing off. Let's see, I need another parenthesis there, I think. No, I guess I was okay. Because these parentheses close, open, close. So we need to divide off a negative 4 times 1 minus y quantity cubed minus 3xy squared. Do it on the right, and then also over here on the left. So negative 4, 1 minus y cubed, quantity cubed, minus 3xy squared. Things are running together here. So then this factor cancels with this one, and we're just left with y prime on the right hand side. So y prime equals 1 plus y cubes on top, and then on the bottom we've got our negative 4 1 minus y quantity cubed minus 3xy squared. Okay, don't simplify. We've solved for y prime. There's still some y's on the right hand side. That's okay. We've got our y prime all by itself on one side. We're done. For test, we're done. Okay, next up we've got a trig limit here. Remember our two trig limits were the limit as theta goes to 0 of sine theta over theta. And then we also had the limit as theta goes to 0, 0, not 1, of 1 minus cosine theta over theta. This limit was 1, and then the bottom limit was 0. And you sometimes also see this as cosine theta minus 1. It doesn't matter if those are switched because it just is the difference of a negative sign on the top and the negative of 0 is 0. So we want to make this limit look like combinations of these guys and maybe sines and cosines. So some of our tools here were things like dividing the top and the bottom by powers of theta, breaking multiplications apart, and that's what I see here is breaking multiplications apart. So I got a 5 on the bottom that I can actually pull that out in front. So this will be limit as theta goes to 0. I can take that 5 out in front as a 1/5. 5 on the bottom is a 1/5 out in front. And then the sine cubed there, I'm going to break that up into 3 pieces here. A sine theta times sine theta times sine theta. And then I've got 2 factors of theta on the bottom. So I'm going to put a theta underneath that sine theta and a theta underneath that one. And here I'm just going to leave a 1. Okay, which I really don't need to write, but if you see, if you multiply across the top, sine times sine times sine is sine cubed. 5 times theta is 5 theta squared. Now why did I do this? Well, sine theta over theta, that matches this pattern. Sine theta over theta, that matches this pattern. And then the limit of sine theta, that we can take that limit by itself. So this sine theta over theta, that is approaching 1. The limit of this sine theta over theta is approaching 1. And then as theta goes to 0. And then as theta goes to 0, sine of theta here, sine theta over 1, approaches 0. Sine of 0 is equal to 0. So since all of these individual limits exist, the limit of the product is going to be the product of the limits. So 1/5 times the limit of this piece, which is 1, times the limit of sine theta over theta here, which is 1, times the limit of sine theta, which is just 0, and this limit is 0. If you see a 1 minus cosine in there, lots of times you've got this multiplying by the conjugate. That happens sometimes. But you want to get it so, this is form 0 over 0, and these are form 0 over 0 too, but we use geometry, or we could use geometry to show this limit's 1 and this limit is 0. You just want to match to those patterns. Okay, next up we're analyzing some motion. So we're given a position, negative t cubed plus 3/2 t squared plus 6t. Want to find our velocity and acceleration. So s prime of t, the first derivative, is equal to the velocity function v of t. So that's going to be, 3 comes down in front, negative 3t squared plus 2 times 3/2. The 2's will cancel, so we'll get 3t plus derivative of 6t is 6. So there's velocity. And then s double prime, the second derivative of position, is our acceleration function, a of t. So 2 times negative 3, negative 6, t, plus derivative 3t is 3. So there's our acceleration function. Here we want to diagram motion showing t and s values. And this says given the following sign diagram. Let's actually make the sign diagram. So to do the sign diagram, remember what you need to do is set your v of t equal to 0. So if we, well, let's go ahead and do that down here. Negative 3t squared plus 3t plus 6, and we set that equals 0. I see a common factor of negative 3 that we can pull out here. So factor out a negative 3, positive t squared is left here. If you factor out a negative 3 there, minus t, and 6 divided by negative 3 is negative 2. And you can double check that, if you multiply back in here times each piece, negative 3 times t squared, negative 3t squared, negative 3 times negative t, positive 3t, negative 3 times negative 2, positive 6. So it's always good to do a double check. And then if this product equals 0, one of the pieces is 0. Negative 3 is never equal 0, so it has to be this piece that equals 0. And that actually factors a little bit more here. So FOIL backwards on this. So we got t and t in the first slots. Factors of negative 2 that add up to negative 1. So it would be minus 2 and plus 1. So t minus 2 is equal to 0, in which case t equals 2. Or the t plus 1 is equal 0, in which case t equals negative 1. Alright, so negative time would be time before the start. We're going to allow negative time here. So let's do a sign chart for V here. So we're going to pick a test number in each of the regions, and then we're going to see, what is the velocity, what's going on with the velocity. So our cutoffs here are at t is negative 1 and t is positive 2. And pick a test number in each region. So less than negative 1, we could test t equals negative 2. Between negative 1 and 2, we could test t equals 0. And t bigger than 2, we could just test t equals 3. So take negative 2, plug that into your velocity function. So plug it in here, or plug it into the factored. So actually here, we could bring that negative 3 down. Then this is the factored version of that. So negative 2 in here, negative 2 times negative 2 minus 2 is negative 4. Negative 2 plus 1 is negative 1. So it's negative 3, negative 4, negative 1. 3 negatives make a negative. Plug a 0 in, we get negative 3. 0 minus 2 is negative. 0 plus 1 is positive. So negative, negative, positive. So that's positive. Plug a 3 in. 3 minus 2, positive. 3 plus 1, positive. Negative, positive, positive is negative. So this thing is going to the left, then it's going to the right, and then it's going back to the left. So now we can diagram the motion here. So we're going to have some turning points here at t equals negative 1 and t equals 2. Generally, we know this it goes left, right, left. So it's going to come to the left, and then it's going to turn around and go back to the right, and then it's going to turn and go back to the left. And the first turning point right here, we know is going to be t equals negative 1. And then the second turning point here, where velocity changes, it changes direction, is going to be t equals 2. So we need to know the s values at those turning points. Remember, this is the s-axis down here. So we want to mark off, what are these positions here and here that correspond to t equals negative 1 and t equals 2. So here we're looking at position, not velocity. So we're going to take the t values and plug them back into the original function. Okay, so we're going all the way back here. So plug in negative 1, we're going to do negative of negative 1 cubed, and then plus 3 halves negative 1 squared. And then plus 6 times negative 1. And if you do those plugins, you will get negative 7 halves. If you do the calculator work here, so negative 7 halves. And then do the same thing, plugging in 2. So this is going to be negative of 2 cubed, like that. And then plus 3 halves times 2 squared. And then plus 6 times 2. And if you do the calculator work there, you get 10. So this position here at t equals 2, that's 10. Can't quite see that very well. So this right here is 10. And then this one right here is negative 7/2. So we know the position, the S coordinate at those turning points. Alright, next up we are given the graph of f, and we want to sketch the graph of f prime. So here's our f, and we want f prime over here. So remember, the thing that makes this go is that the slope of the tangent on f is the y value on f prime. Okay, so m tan on the function f equals the y value on your f prime graph. So you draw tangent segments here. Well, between 0 and 1, this graph is a line, so the tangent segment is just going to be exactly that line. And the slope of this line here is fall 2, run 1. So right here, m equals negative 2. Well, what that means is between 0 and 1 over here, we're going to be at y value negative 2. Now, here it looks like our graph ends, and I didn't extend it past that point, so we won't assume that the function is defined there. I actually probably should have, put an open circle here, and then, put an open circle there. So what that means here is that, okay, the function's not defined, so derivative can't be defined here. This is our graph. This is f, y equals f of x. And then over here we want y equals f prime of x. So let's see, down here we've got a cusp on the graph at x equals 1. So derivative's not going to exist there, so it's going to be open circle down there. And then between x's 1 and 2, the graph is another line, and so the slope of the tangent is going to be the same as the slope of that line, which is rise 3, run 1. So in here, your m is equal to 3. So that's between 1 and 2. So between 1 and 2, our y value is going to go up here to 3. And again, we'll have an open circle on each side here. There and right there. Okay, then we got another cusp. Derivative doesn't exist at a cusp, so open circle. And now our slopes of tangents are negative here, all the way up to right here at 3.5. Right there we've got m equals 0. So our little tangent segment looks like this. So here m equals 0. So that means at 3.5 over here we've got a y value of 0. And then here, notice that if we drew our little tangent segments in here, that they go down from left to right. And you can just estimate the slopes. This one, here it looks like that's, maybe you've got a slope of -1, so fall 1, run 1. And that hits at about 2.5. So at 2.5 here, your y value is probably down here. And that's m is -1. So here, this is m equals -1. And then in here, you could estimate your tangent slope. It looks like it's about rise 1, run 1. So here it looks like m is about +1. That's at about 4.5. So at 4.5, we're at about +1. And then these guys look like they're on a line here. Okay, so it looks like that's a line. In fact, this looks like part of an x squared curve. So if you differentiate an x squared curve, you should get an x curve, because the exponent goes down 1, which would be a line. So here, up here, when you get close to that cusp, which is close to x equals 2, so that's close to down here, our slope is more negative. it's it's steeper, so we could sketch a little tangent segment there. But here you're just sketching f prime, so I'm not going to be real particular. If you have it close. So again, and then up here close to x equals 5, our our tangent lines are going to be steeper, maybe slope of 2, something like that. But we'll just assume that this is a straight line here that goes through these points. And then we'll do an open circle above x equals 5. That's not quite a straight line here. I'll use my line tool. Okay, there we go. That's pretty close to a straight line. And then we'll have an open circle at both ends at 2. And then also at 5. Because we've got a cusp corner on the graph, so the derivative doesn't exist. So I'd have an open circle here and an open circle there. Now, if you did a little bit more with slope, you might decide that that maybe this slope got steeper and this should be up a little bit higher, but we're not going to be real picky about that. If I see you, sketch some slope segments here and then transfer them over and the y values correspond to the slopes of the little segments that you've got here, then we are in good shape. So, but remember these key, especially now this one had some couple of easy spots on it really because it had 2 straight lines. But remember, if you've got a function that's not made up of straight line pieces and it just kind of moves around here, remember that the critical places to sketch your slope segments are here when slope is 0. That gives you a y value of 0 on f prime. And then we just look in here, we see that our slopes are negative. And so here the y values are negative. And then over here we can see that our slopes are positive, like this one. They go up from left to right. And then between 3.5 and 5, our y values are positive. Okay, so that's the important thing, that you find out where slope is 0, where it's positive, and where it's negative. All right, last up we have a related rate problem here. So let's read through this and just kind of take it slow. So you got a friend and you're going caving, and they lower you down into this vertical cave opening, and then they pull out the rope and they tie a lantern onto it and lower it back down to you. Okay, you are 6 feet tall and you back away from the lantern as it's coming down. I mean, you wouldn't want to get hit in the head, right? And the lantern's coming down at a rate of 1 foot per second. And you want to know how fast is the length of the shadow changing, your shadow, on the horizontal cave floor when the lantern is 4 feet above your head and you're 8 feet away from it horizontally. Okay, well, let's sketch a picture here. Okay, so here's the rope, and you've got the light source on the end of the rope, the lantern. We'll just make it a point light source. Okay, and let's drop a perpendicular down to the cave floor. And let's see here. You are here. Okay, watching that lantern come down, but you are also backing up here. Okay, so you're backing up. You're moving this way as that lamp comes down, and the lamp is moving down this way. So that's what's going on. You're 6 feet tall, so let's draw a vertical segment here, and that's going to be 6 feet tall. And that lamp's going to cast a shadow over your head. Well, the line of sight's going to go over your head, and that's going to cast a shadow on the floor here. So what are the things that are changing in here? Well, this length is changing here, the height of the light above the floor. This distance is changing, the distance that you are from being straight underneath the lantern. And then this distance, the shadow length, those are changing. Okay, let's identify those in the problem. So let's see, you're 6 feet tall and you back away from the lantern at 2 feet per second. That's a rate. Okay, so you're backing away, you're moving. And let's go ahead and label some quantities on here. Let's let the distance that you are from being straight underneath the lantern, let's let that be x. So then this rate is saying that dx dt, here's what we know. We know that dx dt is going to be equal to 2 feet per second. And it's positive because as you back up this way, this length is increasing. X is increasing. And your friend lowers the lantern down at a rate. A rate is a derivative of 1 foot per second. Okay, so this length's changing. Let's label that. Let's call that h. And dh dt is the height is actually decreasing at 1 foot per second. So dh dt is going to be -1. Okay, because it's decreasing. And then they ask, how fast is the length of your shadow changing on the floor? Okay, so how fast is your shadow changing? The length of your shadow is right here. Okay, so let's label that length S. And that's what we want. We want the rate of change of your shadow, which is ds dt. And we want that at the instant that the lantern is 4 feet above your head and you're 8 feet away. So you're 6 feet tall. If the lantern's 4 more feet above your head, that means that it's the total height is going to be 10. So we want ds dt when h equals 10. And again, that 10 is 6 plus 4, your height, and then 4 feet above. And when you're 8 feet away, x is the number of feet away. So when x equals 8. So we've got the known rates, we've got the rate that we want written down, we've got a labeled picture. So now we need to decide what are the relationships in the problems. And here, when we are talking about shadows, remember I told you shadows are usually a clue that we are looking at similar triangles. And in fact, these are both right triangles. So the ratio of height to base for the small triangle will equal height to base for the larger triangle. So height to base for the small triangle is going to be 6 over s equals height to base for the large triangle, which is h over x plus s, because the base for the larger triangle is both the distance you're away from the lantern plus the length of the shadow. And then we want ds dt, so we want to solve this relationship for x. We don't want to differentiate it the way it is because it's kind of messy. So let's multiply through by the LCD or set our cross products equal. So 6 times the quantity x plus s here is going to equal s times h. And let's go ahead and multiply our 6 in. So 6x plus 6s equals sh. Now let's bring the 6s over here on the right as a negative, because we want to get our s terms on the same side. So 6x is going to equal sh minus 6s. Now we've got a common s here on the right hand side. Can factor that out. S times the quantity h minus 6. H is left here, negative 6 is left here, is equal to 6x. And we want to solve for s. It's multiplied by h minus 6, so let's divide that off on both sides. And then these guys cancel, and we are left with s equals 6x over h minus 6. Now, x and h are functions. Those are functions of time, and we know the rates of change of x and h. Okay, so what we can do here is we can consider this as a function f and the bottom as a function g, and we can use the quotient rule. So if we do that, then our ds dt is going to be f prime g, so quotient rule, f prime g minus f g prime all over g squared. So f prime is the derivative of the top. Now remember, x is not the independent variable, t is. So the derivative of x is not 1, it's dx dt. Okay, so the derivative of 6x is going to be 6 times dx dt. Now we don't have to use a product rule on 6 times x, even though x is a function, because the derivative of a constant times a function is that constant times the derivative of the function. So there's our f prime, and then our g is h minus 6 minus f, which is 6x, and then times g prime, the derivative of this bottom. Derivative of h is not 1, it's dh dt, and then the derivative of 6 is 0. And then we are dividing everything by g squared, so h minus 6 squared. And then we plug in all of our known values. So we know our rates of change, and then we want to know what is ds dt when h equals 10 and x equals 8. So at h equals 10 and x equals 8, we get 6 times dx dt, which is 2, times h minus 6. Now h is 10, so this will be 10 minus 6, which is 4, minus 6x dh dt, so 6, times x, which is 8, and then times dh dt, which is negative 1, and then divide everything by h minus 6 squared. Well, h is 10, so 10 minus 6 is 4, so that's 4 squared. So this is now 6 times 2 is 12, 4 times 12 is 48, double negative here makes a positive, plus another 48, that's 96, over 4 squared is 16, and that actually goes in 6 times. So ds dt is equal to 6, and our rates are in feet per second, so we don't want to forget our units. 6 feet per second. And we got it. So here we had actually 3 variables, but we knew the 2 rates of change, so we didn't have to try and find another relationship and solve and substitute. But remember, if you have 3 variables and you only know 1 rate of change and you want 1 rate, then you need to be looking for another relationship. Now, you're not going to have to remember any really strange formulas. Probably things that you need to know are, you need to know area is length times width for a rectangle. You should know area of a triangle, 1/2 base times height. You should know Pythagorean theorem, certainly. Area, the surface area and the volume of a cone, those I would give to you. Surface area and volume of a sphere, I think those are more common. So the volume of a sphere, remember, is 4/3 pi r cubed. Okay, so that one you should remember. And then the surface area of a sphere is 4 pi r squared. Okay, this is for a sphere. Okay. And then you need to know Pythagorean theorem I mentioned, so x squared plus y squared equals z squared for right triangles. You need to know similar triangles. So you should be able to recognize that relationship, similar triangles. Just trying to give an idea of the kind of relationships here. Area is length times width. Need to know that one. Volume of a rectangular box. Volume is length times width times height. So those are some of the basic ones. But if you need the volume of something unusual like a cone, a cylinder, a pyramid, some type of shape like that we don't use very much, those volume and surface area, I would give those formulas to you. But these guys here you need to know. Oh, also area of a triangle. For a triangle here, area is 1/2 base times height. Okay, so these are the ones that you need to know. Anything else, if it uses a formula, then I would give it to you. If it involves, labeling triangles and stuff, that's part of the problem. So this is just one representative problem. This isn't, this is an area where I'm giving you one representative problem. You really need to go back and, review your homework from that section and look over the examples in the notes and make sure that you understand those. And I would even, recommend, practicing on some other odd-numbered problems that are similar to the problems that I assigned in homework, so that you've got enough practice on these that you can identify all of the common relationships. All right, I think that's a wrap.